Sorry about that. I'm back. Remember, family is like the most important thing. Okay, family, health, then school, then work, and stuff like that. Take care of yourselves. Take care of your families. All right. Let's see. Y equals x squared plus 2, and y equals negative x on 0 to 1. So we have little axes for us to graph each of these, and it's more to get a picture of what's going on, because then we're going to have to do some algebra to solve it. So x squared plus 2, let's see, 1, 2, that's going to be like this. Y equals negative x, that's one of these. It says from 0 to 1, so here's 0, here's 1. And so this intersecting region that we're looking for, this shaded region is going to be this thing right here. So if we want to find this area, we really, all we have to do is take the top minus the bottom. And this is going to be my procedure for all of these things when we know the interval that we care about. So all I'm going to have to do is go, okay, well, my interval's from 0 to 1, and I'm just taking x squared plus 2, and I'm subtracting negative x dx. I do not even have to care that I didn't simplify any of that. My calculator can handle all of that. Honestly, I'd prefer to simplify it, so I'm going to, because I feel like I'm going to make a mistake in the calculator instead of making a mistake by hand. And I got that, but remember, we can use the calculator to pretend that we did this by hand by pushing the math button, turn it to a fraction, 17/6. Okay. And there's our answer. If you do top minus bottom on the interval, that literally is all we have to do. Let's say we don't know the interval though. Let's say instead, y equals 7. All right, y equals, remember y equals is a horizontal line, x equals is a vertical line. Real quick explanation for this. The reason this is a horizontal line is this is a y equals line. This is saying every single dot ever that has a y coordinate of 7. Well, where's the y coordinate 7? Up here, right? Okay. Where else is a y coordinate of 7? Here. Where else? Here. Where else? Here. Where else? Here. All of these dots have a y coordinate of 7, and so we can just draw a horizontal line saying all those dots. Okay. X equals negative 2. When we go to the x coordinate negative 2, here's one. What's my x coordinate here? Negative 2, negative 2, negative 2, negative 2, negative 2. All these. All right, y equals x cubed minus 1. Okay, so that's down here. It's our normal x cubed graph. It's our swoopy graph like that, but move down 1. So it's going to look something like this. And no, I don't know where it's touching, but if we're looking for this shaded region, we're looking for, I got to find the farthest left it's going to get. And look at that. It's touching down here. It's touching the x equals negative 2. So I already do know I'm going to go from negative 2. And I don't know where I'm going to end yet. I'm going to have to find that. It's going to be there because we're going from left to right. And the other thing, oh, excuse me, I held back a sneeze and spat out a yawn. We need to find that x coordinate. But we can look at this and we can see, okay, we're going to do top minus bottom. Well, the top is this y equals 7, and the bottom is going to be this x cubed minus 1 dx. So now we've got to go search for this upper bound. Let's see, the upper bound, that's the y coordinate when x cubed minus 1 and 7 are touching. So we can say, well, hey, when do x cubed minus 1 and 7 equal the same thing? Well, we can add the 1 to both sides, get x cubed is equal to 8, cube root it, and get x is equal to 2. So it turned out to be that simple that we were just going from negative 2 to 2. I expect that you're able to do these sorts of things by hand. And if I go back on my word and do something in the calculator in this notes, I'll make sure to yell at me right now. So let's see. Let's knock it out. So again, we could do this integral by hand. It's good to have some calculator practice though. This time I'm being more responsible with my parentheses. All right. So that should be good. Let's see. I want to make sure that I actually didn't, I feel like I closed too many. Let's see. Open, open, close, close. That one shouldn't, one of these shouldn't be there. Okay. I got exactly 32. That's a nice satisfying answer. So, to differentiate between this one and this one we were given a boundary. We were said go from 0 to 1. This one we were saying, hey, we don't know the boundary. We're going to need to find it. So that's what our next one's going to be as well. Find the area bounded by the graphs 2 minus x squared and x. So, or y equals x. So our first one is, just a diagonal line. I missed, but hopefully you understand. And then the other one is just an upside down parabola. And we knew that because of the negative x squared. So this time, we're still going to be doing top minus bottom, but we don't know the left or the right. And so this is where we can say, okay, well, I know 2 minus x squared needs to equal x. So I'm going to set this equal to 0, and then I'm going to solve it. Well, sorry. I'm going to move everything so that there's a 0 on one side and then everything else is on the other side. The reason I'm doing that, unlike this last one only had x cubed and a bunch of numbers. This one has x squared and an x. Whenever there's multiple powers of x, generally factoring is going to be the only way that we have to handle it. There are exceptions to this, but in general, that's what we're going to do. So I see the negative x squared. I don't like that. I'm going to add x squared to both sides. And I'm going to subtract 2 from both sides. So that's a positive x, and that's a minus 2. And now it's an equal 0. And so in order to solve this and find these two x coordinates, I'm going to have to solve this. And I could use quadratic formula. I could use factoring. I see the factoring for this, so I'm going to factor it. This is where I'm looking and I'm trying to see, okay, two numbers that multiply to negative 2 and add up to the coefficient of x, which is 1. So two numbers that multiply to negative 2 are 2 and 1, and I've got to put a negative on one of those. And to figure that out, I'm going, okay, well, I need them to add up to positive 1. That means that if 2 was negative and 1 was positive, then I'd get a negative 1. I don't want that. I want a positive 1. So I'll need 2 to be positive and 1 to be negative. So if I do that, now I can solve this. Say x plus 2, you need to equal 0. X minus 1, you need to equal 0. Remember, the only way factoring works for solving is if it equals 0. If it equals something else, then your whole life is a lie, and it didn't work. So, and we've talked about that in class a little bit, why it doesn't work. I'm not going to get into that now. But so x is equal to negative 2, x is equal to 1. So those are our two x coordinates. That means negative 2, 1, cool. Let's say you're totally lost. Just a reminder, you can absolutely, especially since we're going to be allowed to use our calculator on these, we can go to our calculator. So my image is not horribly inaccurate, and I can do second calc and go down to intersect. So if I want to find this intersection, notice how I move the cursor over near it. If I put the cursor in the middle, it's going to decide what it wants to do. I don't want to give it a choice. So I'm going to put the cursor like over past all the intersection points. First curve, second curve, guess. And I hit enter on each of those, and you'll see that the x coordinate they intersect is negative 2. And then we can redo this. Second, so again, we can go second calc, go down to intersect. So if I just kind of leave it in the middle here, and I push enter those 3 times, it goes back to negative 2. And it's like, no, I don't want you to do that one. I've already looked at that one. So what I do is I go over here, click intersect. I want to move the cursor so that it's beyond the other one. Because what happens is, as soon as you tell it to start looking, it just starts plugging in numbers, and it goes, okay, when do our y coordinates match? And it just keeps on going, and it kind of moves out and it tries to find it. So since we're going to move out from here, the first one it can possibly hit is that one. If I put it in the middle, it kind of has a choice. So I don't want to give it a choice. I move a little bit past. First curve, I hit enter. Second curve, I hit enter. Guess, I hit enter. Intersection of 1. The y coordinate is the y coordinate they're intersecting. That's not as important. So especially for finding this region, right? So now we're going to find the intersection from negative 2 to 1 of top minus bottom. So that's our 2 minus x squared minus x dx. And I can go to my calculator and say, hey, calculator, ooh, I'm going to use the shortcut that we've learned in class. I'm going to say, hey, calculator, go to do an integral from -2 to 1. And I need you to, I'm going to use y1 minus y2, right? That's the order I did things. So if I go in, I can say alpha calc y1 minus alpha calc y2. And remember, if your calculator can't do the cool little F1, 2, 3, 4, 5 thing that I can do, if you push the vars button, you can go directly into yvars and do function and pull y1 and y2 out that way. A little bit more button presses at that point, maybe not as helpful, but all right, I got 4.5, which is exactly 9/2. All right, so let's go to the next one. E to the x, remember that's a swoop, right? Whoop. X equals -1, whoop. And y is equal to 8. Whoop. So if we want the region bounded by this, notice for all of these, I'm drawing the picture first and trying to find the region first before I go and do anything else. Okay, so, and I already know when I do my integral, well, if I look at this top minus bottom, well, 8's the top, e to the x is the bottom. I just have to figure out the bounds now. Since one of our things here was a straight up and down line, -1, that's actually going to be our left bound, right? So -1, and we just got to figure out the right bound. And our right bound is, hey, when does 8 equal e to the x? And this is where we can use a logarithm to get rid of the e to the x. I could say log base e of 8 is equal to log base e of e to the x. I can log both sides. But we don't traditionally write log base e. We generally write ln. So ln 8, this is just a synonym for that. And then ln e to the x. So then if I keep on going, well, I can bring the x out front of this and say ln 8 is equal to x ln e using log properties. And if you remember, ln e is just 1 because it's e to what power gets me e, and the answer is just 1. So ln 8 is equal to x. All these steps were not necessary if you remember that you can rewrite this as a natural log. But I know that some of us have kind of struggled with logs so far, so I wanted to kind of tiptoe through it. So let's see, we got our ln 8. This is actually a really nice problem to do by hand, so I'm gonna get the exact answer going by hand. But we could just go to our calculator, but this illustrates a couple of things that I think are beneficial. So when we plug this in, we get 8x minus e to the x. And if we think about that, the derivative of 8x minus e to the x gets us back to that, because the 8x turns into 8, minus e to the x's derivative is itself, so its integral is itself, and the x is just normal, so there's no special derivative popping out there. So -1 to ln 8. This is actually really, really nice. I know it doesn't look like that, but just bear with me. So we get 8 ln 8 minus e to the ln 8 minus -8 minus e to the negative x. So, and if we're careful here, let's see, e to the ln 8, this is a special property that turns into regular 8. And so we wind up getting 8 ln 8 minus 8 plus 8 plus e to the negative x. And so here, those cancel. We get 8 ln 8 plus 1 over e to the x. Oh, whoa. That was a 1, sorry. That was a 1 here. E to the negative 1, that's just 1 over e. So it's 8 ln 8 plus 1 over e. 8 ln 8 plus 1 over e. So maybe I was wrong. It might not be like really nice, but it's not as bad as it could be. And I'll just go through and do the calculator way just to verify that I didn't mess something else up, because I did mess that up. The cool thing is I can go here and type in ln 8 in my bound, and it's totally fine with that. So I'm going to do 8 minus e to the x. So let's see, 8 minus e to the x dx. Cool, okay, so I did it right. Something else that we should probably talk about here, it is possible that I drew this wrong. Especially for something like e to the x where people are not as experienced and comfortable with what it looks like. For these problems where we're allowed to use our calculator, if we're trying to be accurate setting the thing, oh, I can't even graph that. These don't let me do x equals lines, so let me just do y equals 8. It's not a bad idea to spend some time and just double check things like this. So, all right. Cool. 4 more. So, all right, so now we get into this right here. Write a setup for the area of the region bounded by these two curves. So if you look here, it looks like they're intersecting at x equals 3 and 7. And then we're going to assume that they just go off forever and don't intersect after that. So I want this shaded region. And there is an element of common sense here. It's always top minus bottom. So that means if they change places, then we need to change our setup. So from 0 to 3, we can see that f of x is on top. So from 0 to 3, we can do f of x minus g of x dx. But then from 3 to 7, notice how f of x dips down and g of x becomes the victor, if being over is the winning, whatever. So then we can do from 3 to 7, and we'd have to do g of x minus f of x. So this is always something to keep in mind and pay attention to. So this example 5 says, find the area of 2 of the intersecting regions when using the curves y equals sine x and cosine x. So if you remember, sine x starts at 0 and swoops up, down, and back up. Let's do 2 periods of it. So it looks something like that. Cosine has 1s everywhere that sine has 0s, and 0s that everywhere sine has 1s. So if I'm being careful, oh, I already have 2 regions right here. So if you remember, we're trying to find these intersections, right? Well, looks like they first intersect right here. And if you know your unit circle, or you can remember your special right triangles, that happens at the isosceles at the 45, 45, 90. So that means that our first intersection here is at pi over 4. And so we can go from pi over 4, and then when do they equal each other again? If we think about our unit circle, they don't equal each other here, because one's positive and one's negative. They equal each other here when they're both negative. That's 5 pi over 4. So it looks like my first one, well, this is sine, and this one's cosine. So that means that we're going to have to do sine minus cosine. And if you're thinking clearly, you might notice the symmetry in these pictures. And that's not wrong. That symmetry is real. That means if I just double this, we should be good. Because that's one of these regions. If I double it, should be that one. But you know, we could say, okay, well, I'm gonna do from 5 pi over 4 till, when do they intersect again? Well, they intersect again when we get back to here. So these wind up being the places where they equal each other, not that. So this one, and this one, right here and here. Wow, I'm just scribbling even more. Anyway, so pi over 4, 5 pi over 4. If you notice, they were 4 pi over 4 apart. That means that 4 more pi over 4 will be the next one, so 9 pi over 4. I could do cosine x minus the sine of x dx. So we can go through, we can type it all in. Make sure you're in radian mode here. You know what? I'll type it in. I'll type it in. Okay. So from pi over 4, and then 5 pi over 4, sine x minus cosine x. And I'm going to do these separately just so you can see that they are in fact the same. I have a feeling that this is some kind of square root. So to kind of check myself, I'm going to square it and turn it into a fraction. Oh, this is the square root of 8. That's fun. All right. I don't expect you guys to know that little trick, but you know, if I think this is a square root of something, I can try squaring it, and then if I get a fraction, I could turn it back into a fraction and find out what fraction it was the square root of. So that one's the square root of 8. Let's find this one. So that's going to be, that's a 9 pi over 4. That's a 5 pi over 4. Do cosine x minus sine x. I'm so surprised it's the same number. So I could say this is 2 root 8, or I can simplify the square root of 8 to 2 root 2. So this is 4 root 2. Or, you know, 5.657. Just know, on the AP exam, if they gave you this question, they would give the exact answer. They wouldn't give you that. All right. The area bounded by this. Okay. 2x plus 4. I knew that one. It's a line. X to the 4th minus 2x squared. Not 100% sure on that one. There's a few different ways that can look. So let's use the calculator. There are really only a few basic shapes that I know the graph of off the top of my head. If it had been x to the 4th by itself, then I know what it looks like. But see this kind of swoop we have there? Okay. Actually, I'm thoroughly confused by this. Why do I have this problem? We do top minus bottom and where they intersect. We've already been through all of this. I don't need to do this question. They don't switch places ever. Let me make sure I typed it in correctly. I did. Maybe it's supposed to be x cubed? No? Oh. Well, you lucked out. We're skipping this one. Next. Again, it's a cubic, not 100% sure where this is going to line up, how many bumps it's going to have, so it's better to just check it out. There we go. Okay. So this is more the stuff that I was talking about. So we've got that region, that region. We're going to have to find this place where they trade places. We're going to have to find all 3 intersection points. So one way to do that is to say, well, x minus 2 needs to equal x cubed minus 4x squared. And last I checked, we don't have a super great way to solve a cubic. It wasn't until I was in college that I learned a formula, and this doesn't actually fit the form that we need for that formula. This is not something that's going to be easily solvable. So this is where we would go to our calculator. So earlier when I was like, I expect you to be able to do this stuff by hand, true, to a point. Oh, missed. All right. That happened because I guess I didn't go far enough. There we go. All right, so our first one is negative 0.762. Our next one, okay, I'm just doing that little intersect trick. I'm going to try to be close to it. Got it. Let's see, 0.637, and last one. $4.125, and so we would just say, hey, from our first one, 0.762 to 0.637. We're going to take g of x minus f of x dx. Then from 0.637 to 4.125, we're going to take f of x minus g of x. And we are allowed, if f and g are defined like that, I'm allowed to show it like that in my work and go and type stuff into my calculator and get it done. I don't need to fancy schmancy write everything out. There's no point. These are well defined within the problem. And I could even give each of these a letter. Like I said, that's A, that's B, that's C, and go from A to B and then from B to C. Totally allowed. As long as I define things, there's no issue here. Oops. 7. So then we're doing y1 minus y2. Let me make sure that I put these in the correct order. So I want the QB minus the line. QB minus line, that'd be 2 minus 1. Then, and yeah, you can just, I'm just going to do it all in one line. Don't even care. 0.637 to 4.125 of, now it's 1 minus 2, right? Line minus curvy, yep, okay. Line minus curvy dx. And I get 24.136. Now, I should not try to simplify this to a fraction right now because this is an approximation off of approximations. It's not great that I stopped at 3 decimal places. If I was using a computer and doing this for a job, I would get a huge decimal for these and go out as far as I could. But this is more for instructive purposes, so I hope it's been helpful. All right, final question. Find the area of the region bounded by the curves f of y is equal to y squared minus 4 and g of y is equal to y minus 1. All right, everyone's favorite, sideways stuff. So, in case you don't know, we can graph y as a function of x. So, I just said that. What I meant to say is x as a function of y. So like as our y value increases, what happens to x? And so we can look at this and we can think about this. This is, if this were x squared minus 4, it'd look like that, right? So if we just kind of take that same idea, okay, its x-intercept is -4, and it's a parabola. There we go. Similarly, y minus 1, its x-intercept is -1. And as our y value increases, our x value increases. And so we're going to have to solve this. Y squared minus 4 is equal to y minus 1. And this is a quadratic, so we can use our quadratic methods and get, y squared minus y, add the 1 to both sides, and get minus 3 is equal, oh boy. I can't factor that. Nothing multiplies to 3 and adds to 1. Nothing nice, at least. So what I'm going to need to do is I'm going to use a quadratic formula. So we got our a is 1, our b is -1, and our c is -3. So let's see. The quadratic formula is -b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So let's see, that's 1 plus or minus, that's 1 plus 12, that's 13 over 2. And so it looks like our two intersection points here are going to be 1 minus the square root of 13 over 2 and 1 plus the square root of 13 over 2. But wait, I hear you asking, Mr. Campbell, those are terrible numbers. I don't care. They're decimals. Fine, get the decimal. Use the decimal. Next, how do I do top minus bottom? Like this. Instead of doing top minus bottom, we're going to do right minus left. So I'm going to do my y minus 1 minus my y squared minus 4 dy. So righty minus lefty dy. So, and that's really it. So our homework, all this junk. I say do the first and last in each section, and the directions regardless are do a little sketch, and the sketch does not need to be more accurate than the ones that I was doing. Set up the integrals by hand, finding these by hand when possible, when you know how. Challenge yourself to do those by hand, and then calculate it. So hope that was helpful. I always want to say see you next time, but I don't see you right now. So how am I going to see you next time? Have a good one.